Good day, ladies and gentlemen. Welcome to another edition of Prometheus University. And this is the fourth part in our series on bending stress analysis and design. And in this part, we'll be talking about the plastic section modulus, usually denoted as ZX. This video is a direct descendant of our first video, so I would advise you to watch the first video on the elastic section modulus, which describes the distribution of bending stresses in a cross-section while we're in the elastic phase. In this part, we'll be talking about the plastic section modulus, which describes the distribution of bending stresses in the plastic or post-elastic phase after the yielding of the material. So to quickly go over again the concept of bending, like in our first video, we talked about a beam with length L, and we applied a force P perpendicular to its length, and we determined that the bent shape, the deformed shape, the red smiley face shape that we have there will be the way the beam deforms. And then we looked closer to see the difference between the blue undeformed beam and the red beam, and we said that it essentially corresponds to a shrinkage at the top corresponding with compression and an elongation at the bottom corresponding with tension. Again, watch the first video for a slower and more thorough explanation and exposition and development of these ideas. Another idea that we introduced in the first video was the relationship between stress and strain. Stress can be thought of as a pressure. It's a force divided by an area, measured in pounds per square inch, PSI, or newtons per square meter, which is called a Pascal, but it in essence is a force divided by an area. Strain, on the other hand, is a unitless way of measuring deformation in mechanics. Strain is essentially a change in length divided by the original length. So if you apply pressure to something, a tensile stress or compressive stress, you change its shape. And we can plot, as you can see here, on the vertical axis, stress denoted as sigma and strain denoted as epsilon. Now, the elastic range is that range wherein there is a linear and reversible relationship between stress and strain, and that's denoted here by the green line. Beyond the elastic range is called the yield point, the point where the material yields and does not return to its original shape when further stressed. And beyond that range is what we call the plastic range. Okay, now so far so good. We haven't introduced anything new. Further, we considered a cross-section of the beam. We considered this beam to be a rectangular cross-section. We gave it parameters such as B and D, B being its breadth and D being its depth. We drew a line through the middle, represented here by the green line, and we called it its neutral axis. And we talked about a stress diagram. Again, watch the first video for a thorough explanation of these ideas. Now, note here, as we mentioned in the first video, that it is experimentally verifiable that there is a linear transition from compressive stress to tensile stress through the cross section of a beam in bending, right? So we have on the top there compressive stresses, which we're denoting as a yield stress. We have reached yield point, and tensile stresses at the bottom. And as you go from the compression to the tension, positive to negative, if you will, we cross zero, and the 0 point is called the neutral axis. But notice, however, that only the top part of the beam has reached yielding. Only the top and the bottom part. The top part in compression and the bottom part in tension. Well, the question is, what happens if we continue to further stress the beam, continue to bend the beam? Now, it is important to note here that for the purposes of most designs, the yield stress is the maximum amount of stress that a material is considered to be able to withstand. But so far, only the top fibers of our material in compression and tension at the top and the bottom respectively has reached yielding. right? So if we imagine, if we continue to bend the beam, continue to stress it, more and more of its cross-section towards the center will reach yielding, right? So we'll get a stress distribution looking like this as we continue to bend it, with the yielding portion denoted here as the purple to match the purple line in our stress strain distribution at the top left, right? And if we continue to stress the beam, continue to bend it, the entire cross section will become purple or will reach yielding, right? And we will get the distribution, the rectangular distribution at the top and the bottom shown to the left here. In our first video, ladies and gentlemen, our task was, or could be described as, given a particular cross section and a particular amount of torque applied to it, what is the bending stress? What is the amount of stress experienced by that cross section? And we developed this section modulus that was able to give us a description of both the stress distribution and the amount of stress. Or conversely, given a particular cross section and knowing the yield stress, what amount of moment can we apply such that the top fibers, the most extreme fibers of the cross section, has reached yielding? In this case, for the plastic section modulus, our task is similar. Here, given a particular cross section and knowing the yield stress of the material, the question is, how much torque, how much moment can we apply to this cross section such that the entire cross section has reached the yield stress? So similar to the first video, we know that this moment M, this torque, right, is made up of the tension and the compression couple, right? So we have tensile stresses and we have compressive stresses, right? And there is a distance between them, and this couple and this lever arm gives us the moment. Now, in order to get the compression, we know that being a rectangular or a square distribution, the compression is going to be located at the middle of the distribution. So we place it there, compression denoted as C, at the middle of the top part, right? That's the resultant compression, right? Taking that entire compressive stress and resolving it into a force. Okay, again, watch the first video for a slower and more thorough explanation of these ideas. Now, and same thing we do for the tension side. We put it at the middle of the tensile distribution, right? Now, the other question is, what's the lever arm between these two forces? So notice that the length of the compressive stress block from the neutral axis, which is the green line, upward is d over 2. Same thing for the tensile stress block. From the neutral axis, which is the green line, downward is also d over 2. And we also mentioned that for a rectangular stress distribution, the resultant is located at the middle. So from the green line up to the compressive resultant C is half of d over 2. Same thing, from the green line down to the tensile resultant T is half of d over 2. So the total distance from C to T is half of d over 2 plus half of d over 2, which gives us d over 2, right? So now we know the distance, the lever arm between the force couple, right? So now let's go further and define the tension and the compression. The tension is equal to the compression due to equilibrium, right? And it will equal to the area of that stress distribution times the width, okay? So the entire area, the entire volume of the stress distribution, if you will. So what is that area? That area is equal to the height of the rectangle, which is d over 2, right? Times what we might call the width of the rectangle, which is the yield stress, times the width of the beam, B, right? So what we have is BD times the yield stress divided by 2. Okay, so the moment, as we have earlier discussed, is equal to the tension or the compression times the lever arm between them. So let's go ahead and define it. The plastic moment, the amount of moment that causes this cross section to reach yielding, the entire cross section to reach yielding, is equal to the tension or the compression, which is BD stress, yield stress, which is gamma Y, divided by 2, right, times the lever arm, which is D over 2. So what we get is gamma BD squared over 4, right? Gamma Y BD squared over 4. And this object here, BD squared over 4, is the plastic section modulus for a rectangular cross section. And this allows us to know exactly how much moment we can apply to a given cross section, in this case a rectangular cross section, that'll cause the entire section to reach its yield stress, right? Similar to the to the elastic section modulus. Now we can go further and say that the plastic moment, the amount of moment you require to yield the entire cross section, is equal to, in general, the yield stress multiplied by Zx. And Zx in this case for a rectangular cross section is BD squared over 4. Now there is a relationship between the plastic section modulus, right, Zx, and the elastic section modulus, Sx. And that relationship is called the shape factor. Basically, it's a number, it's a ratio that tells you how much greater the plastic section modulus is compared to the elastic section modulus, right? So in this case, if you compare BD squared over 4, which is the plastic section modulus of a rectangular cross section, with BD squared over 6, which we derived as the elastic section modulus of a rectangular section in our first video, we see that there is a relationship of 1.5. Okay, there is a 1.5 relationship between the two. So after the first top fibers of a rectangular cross section have reached yield stress, you can add 50% more stress, 50% more torque to that material in order to completely yield the entire cross section. Now we'll discuss ideas like this plastic section and what it's used for in design, and elastic section modulus, how it's used in design, and the shape factor and other things when we touch upon more design oriented topics in the following videos. We're going to talk about how plastic section modulus is used in steel, how the elastic section modulus is used in wood design, and so on and so forth, and ideas about stability, which will lead us to talk about compression, and so on and so forth. But once again, I would like to thank you very much, ladies and gentlemen, for spending your very precious time to watch this video, part 4 in our series on bending stress analysis and design. And if you like what you see, please subscribe to our videos and spread the word, and watch out for more videos in this series and other series coming at you in the near future. Thank you very much.